Hi, good afternoon, everyone. Thank you for being here. I'm Mustafa Samir today. So, I will be presenting my work today and how it becomes a single dissertation direction. So, my central message is modeling resolution is not neutral, it changes decision. And the transition is I will start with a quick roadmap of the talk. So I will cover four parts. The first one is the motivation, and the second part is the trust, which having the resolution or flood risk in Lumberton, and the thrust to second thrust is will be the wind drive and rain intrusion through sliding glass doors, and also my dissertation plan and alignment with the committee. So throughout, I will highlight the decision impacts, how modeling choices propagate to loss estimates and therefore to mitigation and policies. So the next slide, I will be discussing about the frame, what I have done so far, and where it goes next. My work is so far has two application thrust, so which connects to one question: how do modeling assumption affect flood risk outcomes and also functional performance of the built environment? So the thrust one quantifies the resolution driven bias in flood loss impact estimates using USGS database and portfolio based on vulnerability model, and the thrust 2 evaluates the wind-driven rain intrusion through sliding glass door systems, linking standards to hurricane realistic demands. So together they support a dissertation focused on multi-hazard decision relevant modeling with transparent uncertainty and defensible data pipelines. So now I will motivate why this matters and why resolution is not just a technical detail. In practice, communities and agencies make decisions using risk metrics such as loss accidents, hotspots, benefit cost, but the inputs are never perfect. Resolution choices that are spatial sampling, portfolio aggregation, exposure detail can introduce systematic bias. So the key point is if the modeling pipeline is resolution sensitive, we can misrank neighborhoods, misestimate losses, and mistarget mitigation dollars as well. So my goal is to produce guidance that is actionable, what to hold constant, what to vary, and what resolution is good enough for a driven decision. So with that, I will introduce Thrust 1, the Lumberton flood loss study. Um, Actually, we have a question in mind that why we choose Lumberton. So Lumberton is a strong case study because it has repeated flooding impacts and a clear need for defensible risk analysis. This trust is designed to isolate the effect of exposure, vulnerability, resolution, not to claim new hydrodynamic simulation. Important clarification is that we did not use hydrodynamic model outputs or FEMA different data. Our hazard and terrain inputs are USGS 3 DEB detail elevation maps and also flood depth rasters that use consistently across scenarios. So the next slide, we will show the workflow and what we keep fixed versus what we vary. So this slide is the mental model that we name because we hold constant such as like study area, USGS DEM, and also flood depth rasters and the building inventory codes. Then we run the resolution experiments. So for example, like resampling terrain or depth grids and varying vulnerability representation. So we extract event depth at buildings and computing depth relevant to FFE for phosphor elevation and then compute event losses as well. And finally, we compare our outcomes using the risk curves and accidents matrices, specifically looking at how results shifts across the resolution. So now I will walk through the computational core that the building level that is we named as the building level loss algorithm. So this is the building level flood loss estimation using the portfolio of archetypes. So algorithm one is known as the engine. Where we have the combination of the depth ratio, and dollar segregation as well. So as we can see that the inputs are the building values, floors floor elevation, archetype assignments. The archetypes are assignments are we create the different types of groups like 15 archetypes, and then from 15 we reduce it to 10, and then from 10 to 7, and then 7 to 4, then 4 to 3, 3 to 1. So there are like six different groups having like different archetype resolution as well. And also we have the event-wise depth at the building. So the step one is usually the computational. So we compute the depth which is used for the vulnerability, sometimes depth above ground, sometimes depth relative to first floor elevation, depending on architect assumption. So, and the step two, which has the gap depth to a consistent physical range for stability and comparability. And the step three is having the usage of depth loss functions to interpolate the loss fractions as well. So in the final stage, like step four, we use the computational building loss in dollars and aggregate across archetypes and archetype groups to produce portfolio losses by events. So the reason this matters is that aggregation structure itself can create bias, even when the hazard is held constant. So that's why we try to produce the portfolio losses by events as well. So the next step is I will show you the hazard inputs and the key idea that the hazard is fixed. We vary the vulnerability representation. So here is the illustrative view of our hazard or terrain inputs. Again, we use the USGS derived terrain, 3D DEP, DEM, and also the flood depth rosters for return periods from frequent to extreme events. So we do not introduce any hydrodynamic solver, or our focus is the risk pipeline sensitivity, not generating new hydraulics. So this setup lets us isolate whether differences in loss are coming from representation choices, not from changing the hazard physics. So as we can see from this picture that different for events for D1, like for 1 year event, and for the 2 year event, for 5 year, 10 year, 25 year, so 50 year to like 1000 year events. So there is a change of the terrain in the flood loss, like from 1 year, as we can see in 25 years it has changes a lot, and also in 1000 year the changes has been significant. So from this we can have a basic assumption, and that it isolates whether the differences in losses are coming from representation choices and not from the hazard physics. So let's get back to the next slide. So here, as we can see that the first major results, the course archetype portfolio systematically distort the estimated losses. So as we can observe that for the first year event, second year, fifth year, 10th year, and then consistently going to the 1000 year events, and we have different archetype patterns as well. For group 6 it has 15 archetypes, then group 5 it has like 10 archetypes, then group 7 has um, um my apologies, group 3 has like 7 archetypes, and group 4 has four, then three, then one archetypes as well. So group five has like one archetypes, and group two has four archetypes. So as we can observe that based on different color scenarios, like this blue represent the group six, and this slightish green represent the group two, and this one represent the group five. So as we can see that When we compared a digital portfolio representation to a simplified one, we observed a large shift on the order of multiple full differences depending on the event frequency and aggregation. So this matters basically because like a decision maker might interpret those differences as real risk changes when it may be modeled resolution bias. So that the key takeaway is from this is the resolution can move the loss curve enough to change what gets prioritized. So um, as we can observe that there are like frequent events are most sensitive like for small depth and the frequent events consist of small depth differences with a combination of non-linear damage and also the aggregation hides the full vulnerability subsets which consist of like phosphor elevation foundation and occupancy and also the bias can affect the uh, BCA insurance and mitigation prioritization as well. So first of all, we get that for 1,000 year event, the total loss is like around 122.62 million. And also for group 5, we can observe that which is 32.73 million. And also in other case, like for 1 year event, the group 6 having like the total loss of 0.31 million. And for group 5 is like 0.02 million. So to again understand the matter, like group 5 having only one archetypes and group 6 is having only 15 archetypes. And in the same case, like for 1,000 year event, group 6 is having only 15 archetypes and group 5 is having only one archetypes as well. So the losses, as we can see, is that it is like 3.7 times much higher in group 6 in rather than group 5. And also in for 1 year event, as we can see that the losses of group 6 is like 15.5 times higher in group than the group 5. That is like 0.02 million. So the next slide, which I will quantify where the bias is largest and how it behaves across the written periods. So here I focused on where the bias peaks. We see the strongest sensitivity often in the more frequent events, where small depth differences and vulnerability representation changes can swing losses. But even at rare extremes, the bias persists. So it's not only a small event problem. The practical interpretation is like if my model is used for planning and investment, so I need a vulnerability representation that matches the decision scale. So as I can observe from the figure is that like for 1 year event and then for 2 year event till the 1,000 year event, there is a little changes drastically like in the events. So as we can see that the strongest sensitivity often in more frequent events like the small depth difference and vulnerability changes can swing the losses. So the key takeaway is like the course portfolio can be conservatively wrong or dangerously wrong depending on decision use. So we need resolution guidance and uncertainty reporting as well. So based on like different patterns. So the next, like we will discuss about the support that I will show the multiple lines of evidence, not just one plot. So these supporting plots tell the same story from different angles. So the risk curves and accidents comparisons as well. So even when the hazard is consistent, the curve shape and ranking can shift because aggregation changes how losses accumulate across the portfolios. So the core contribution is not a single number. It's a diagnosis of sensitivity and a transparent set of outputs that reveal where decision can be unstable as well. So as we can see from the sensitivity heat map and also in the accidents curve and also in the loss curve function as well. So if we can see a little bit from this, we can understand the scenarios as well. So if we can zoom a little bit further, so as we can see that the loss versus in written period of archetype groups, these are the total losses in millions, and these are the written periods. So for group 6, as we can see that it's 122.2 million losses in case of like for 1000-year events. And also as we can see, the lowest one, which has like the group 5, is very low in comparative to the 1000-year events for the group 6. So also like for the other case in loss accidents curves of different archetypes groups, we can see that the annual accidents probability versus loss in millions. So in case of archetypes accidents, and so thus we can observe that the core contribution is not a single number, it's a diagnosis of a sensitivity and a transparent set of outputs that reveal where decisions can be unstable as well. So now I translate these findings into a decision-ready guidance, what practitioners should actually do. So this slide is actually my value add beyond running a model. So I propose a resolution error workflow, which runs a small set of resolution scenarios which quantify stability of key decisions and report uncertainty bands rather than a single deterministic loss. So the guidance example is if my decision in is neighborhood prioritization, so I must ensure that my vulnerability representation is stable at that scale. If not, my ranking is not defensible. So the key message is like don't report a single loss number, whether report sensitivity and decision robustness as well. So, from this, as we can observe that defining the decision, which having consist of like a screening, benefit, cost, and insurance are designed, so the error may be acceptable. But if we start with a smart portfolio, but make it strategic, separation from separate foundations, or first floor elevation occupancy that drive loss, and also we have like to run a resolution sensitivity check, we should compare the cores versus final portfolios like for 2 to 3 representative return periods as well. And then we report the bias or uncertainty explicitly, like a portfolio definition having a combination with expected under or overestimated estimation of bands. So from this third one, the statement should be like the exposure vulnerability resolution is a controllable modeling lever. So we should quantify and report its introduced bias as well. And now I will shift to the third tool, which is the wind drive and rain intrusion. So this technical paper that we have worked on with the Florida Building Commission, and it was like submitted on last year in December for the final revision, and they accepted the paper, technical paper. So, I mean, it focuses on the post-hazard functionality from different mechanisms and wind-driven rain intrusion through sliding glass doors. So this is very important because the intrusion can drive loss of habitability, downtime, and cascading impacts even without structural failures. So the contribution is to connect the standards and test methods to hurricane realistic treatment and identify where particles may under or over represent risk. So this support the wind resilience decision and building code improvements. So we have like stand we have like um, we have some codes and standards that we reviewed while during through the process. So we have like NAVs and the TAS 202, ASTM E331, E547, and post hurricane observation. We use the FEMA um, and met reports as well. And for the experimental evidence, we included the World of Winds reports as well from Dr. Chaudhary as well. So we had so the problems we addressed during the technical report writing is like the wind-driven intrusion can cause the content damage, molds, and costly downtime even without structural failures. And the sliding glass doors are vulnerable because like the tracks and drainage paths may be overwhelmed. So the next I will motivate that I will explain the gap between the standard test and what hurricanes deliver. So even drive-in intrusion, um, uh, just apply control pressure and spray, but real storms bring the gustiness like angle changes and complex exposure conditions. So the key research question is like, do current test protocols represent the boundary condition that matters to for real performance? So the outputs out of this trust is like code relevant. It provides evidence on likely failure models, sensitivity to configuration, and guidance for improving the test realism. So the work complements thrust one, like both are about like decision relevant modeling under uncertainty. So uh, when we reviewed the standards like for NAVs, water penetration testing requirements for the PG dependent, and also TAS 2002 202 water intrusion procedures. So as we can see that there's like 50%, like 15% DP concepts as well, deep penetration concepts, and also like when we reviewed the ESTM E331 uniform and ESTM E547 cyclic water penetration tests as well. So we observe from this that from the literature that the lab tests are largely steady or simplified. Hurricanes are unsteady, multidirectional, multi-phase, and duration dependent as well. So my dissertation theme is resolution error decision ready multi-hazard risk and functionality modeling. So the flood thirst quantifies the sensitivity in loss estimation in pipelines using the national data sets and portfolio vulnerability representation. So we have like the wind driven run intrusion trust linking with the building components performance and test realism to functionality and recovery outcomes. So together they support a unified framework, transparent assumptions, reproducible workflows, and outputs that directly support the mitigation and code decision as well. So as we can see that we are linking the flood risk modeling with the wind driven run intrusion. So the resolution knob in our flood risk is the archetypes and the portfolio size. So archetype portfolio size is like from 15 to 1 archetypes. We try to create a various groups as well. And also for here is for the wind driven rain intrusion, we have the realism of the load protocol. So the output of the flood risk modeling consisting of like combination of the event losses and accidents curve. But here the driven when intrusion output containing of the whether it should be passed or whether the test should be failed by in a combination of the leakage matrices as well. For the decision risk, as we can see that for the flood risk modeling, we have the unpreparedness and misprioritization mitigation. But for the decision risk for the wind driven rain intrusion, we have like a false confidence in compliance. So our dissertation aims should be like for the aim one, we have the quantify and generalize exposure, which is having the vulnerability aggregation bias across communities and hazard severities. And for the aim 2, we have developed the decision rules to pick minimum sufficient resolution and communicate uncertainty transparently. And for the aim 3, we have like the extending of the resolution concept to hurricane wind driven rain intrusion in demand, and also which is having the improved test guidance tied to climate adjusted maps as well. So the next I will show how this align with the committee's expertise, because I want the feedback of each committee members to strengthen my dissertation, final dissertation. So so I have mapped my dissertation task to the committee's strength for flood risk and uncertainty. I will leverage feedbacks on sensitivity analysis, exposure and vulnerability modeling choices, and defensive risk matrices. And for structure and functionality modeling, I will align the damage to function links and recovery interpretation with resilience-based practices. And for experimental or standard works, I will use input on protocol designs, performance matrices, and how to communicate my findings to good stakeholders. And my final goal is that each committee member sees a clear line from their expertise to a dissertation chapter. So finally, I will preview the questions and I will expect how I am prepared to answer them. So these are all the things that I have prepared for myself based on different committee members' expertise. So first of all, here is my the advisor, Dr. Umar. So his research is more on flood and hurricane risk, community and resilience, fragility and growth modeling. So my aim one and two is directly related with his research, and as per like with Dr. Anand. So our research is based on wind engineering and wind effects and also the large scale wind testing. So my wind drive and wind intrusion demand and also having the testing protocol evaluation, which is in three, is directly related with her research. And with Dr. Zisis, as his expertise is based on like structural and environmental wind engineering, testing and monitoring. So I think my aim three also in where like the rain interaction measurement and performance metrics is directly related with his research, and with Dr. Elzono as his research is more on sustainability, resilient infrastructure construction, and project management. So I think my aim two, which is bit like and related with the decision communication and PCA implications and implementation pathways is directly related with Dr. Alzheimer's topics of research as well. So finally, I would like to thank for your time and for the feedback. And I welcome questions, especially on strengthening my dissertation scope, novelty, and most impactful next experiments analysis. So thank you so much for your wonderful, valuable time. So I really appreciate any questions or feedback that you have regarding with my question with the presentation. Thank you so much and have a wonderful day.